Good evening, everyone. My name is Adolfo Malabanit, and today I'm going to be going over the APPC gravity problem that we did in class, or this is basically the quiz process on how to solve this problem. So let's just read out the problem first. A spherical, non-rotating planet has a radius of r and a uniform density throughout its volume. Suppose a narrow tunnel was drilled through the planet along one of its diameters, as shown in the figure above, in which a small ball, mass of m, could move freely under the influence of gravity. Let r be the distance from the ball from the center of the planet. So let's tackle the first part of the problem. Show that the magnitude of the force on the ball at a distance, small r, is less than big R from the center of the planet is given by the equation F is equal to negative CR, where C is equal to 4/3 pi g density multiplied by mass. So let's start off with that first problem. Since this is a gravitation problem, or it deals with gravity, we could represent it through using the universal gravitation equation. However, we can't keep this for the entire, you can't use universal gravitation for everything, as I will explain later. So just as a standoff, just to start off, we have our force is equal to negative big G m1 multiplied by m2 over r squared. And as you see here, I put a negative as using the right-hand rule, since the ball is going inside of the planet, or it's going towards the center of the planet, following the left-hand rule, this quantity would be negative. So in order to get from this equation, in order to get the F is equal to negative CR, we first need to understand the relationship between mass and density and volume. So the equation here is that we have mass is equal to the density of an object multiplied by its volume. And in this case, we're looking at the mass, density, and volume of the sphere. So we were given the variable for density, and we have to multiply it by the volume of a sphere, which is 4/3 pi r cubed. Substituting back that into the force equation, we have negative g m1 4/3 pi r cubed multiplied by density over r squared. Through canceling out the r squared on the bottom, we are able to get F is equal to negative 4/3 pi r, the gravitational constant, the mass of the ball, or m1, and then density. And then using the variable c in order to represent this whole this 4/3 pi r, using the 4/3 pi g density and mass, we are able to get F is equal to negative CR. And this is very, very interesting to note, as it actually has a lot of similarities to the spring constant equation, or if you were to measure the force of a spring, F is equal to negative kx. So a little bit of foreshadowing for the following problem. Next, what they wanted us to do is sketch the force F on the ball as a function of distance r from the center of the planet. So what we need to realize here is that, unlike every other universal gravitation problem that we've done in the past, or that a lot of AP Physics 1 students have done in the past, is that in this case the ball is going inside of the object, as shown by my little diagram here. Sorry if it's not focused or you can't really see the arrows, but as you can see here, we have a ball going within the planet. So the reason why this is significant is that mass is not only in the center of an object, as stated within the problem, its density was uniform, meaning that when the ball is going within the little tunnel passage, forces are going to be going all around it, leading to an oscillation of sorts. So as we see here, as you drop the ball within the little hole, it'll follow a normal path of force that's being applied to the object, as it's negative as it's going inside of the object. However, due to the fact that there's mass surrounding the ball, and due to the fact there's going to be forces that are going to be pushing the ball from all directions, causing a sort of oscillation here. So as we see here, it goes down linearly, and then it has a little bit of a curve as we keep on going. And if you were to keep on going, it would be an oscillation wave type of movement. So that's just our little sketch of the graph. Let me just put F here. And then this is the total radius, or the distance traveled. So moving on to part C, determine the work done by gravity as the ball moves from the surface to the center of the planet. So using our initial equation, we have work is equal to force, which is a vector quantity, multiplied by the total distance, or the change in distance, delta x, which is also a vector quantity. So we've already established that force in this equation is represented by negative CR, and then we're just going to keep that delta x. However, what we need to note here is that because the radius, or the radii of the radius is constantly changing since the ball is moving towards the center of the planet, that means it's not constant. And that's actually important because work is a quantity that relies on distance. So if that's constantly changing, we need to account for that. What we can feign to do is that we could take the integral of this function. As if we take the integral, we're accounting for an infinite amount of small sums. We're taking an infinite amount of that. We're recording the infinite amount of distances that are traveled, or that overall infinite amount of changes of distances, and overall this sum will allow us to find the total work. So we have to integrate it from the bounds from 0, which we're assuming to be the surface, to the radius, so big R, the radius, as seen here. So using some integration, using the power rule, you add c is a constant and r is our variable. So we square this, divide it by 2, and then we were to evaluate it from the bounds from 0 to r. And then I'm not going to show the substitution. However, if we were to substitute it, the 0 term would cancel out, that you'd be subtracting on the right side. There would be another term we'd be subtracting it. However, we're going to get work is equal to c capital R squared over 2. Next question is determine the speed of the ball as it reaches the center of the planet. So what we have to realize is that this is an energy question, as we're assuming that air resistance is negligible. So we have potential energy of a gravitational force is equal to mgh, and our forces, of course, is equal to negative cr. That's a recurring thing that to keep in mind when completing this problem. So if we assume that the force is also similar to mg, as it's a gravitational force, we're able to say that PE is equal to FH, as we just substitute this mg value for F. So from there, since we know that there's no energy loss, we know that PE, oh my god, that's a bad E, but yeah, we have PE is equal to KE. So we take the amount of work done, negative CR, and we set that equal to 1/2 mv squared, as PE and KE are equal in this scenario, and thus we can set them equal as such. Through taking the derivative of this, which we've got in the previous solution, we have CR squared over 2 is equal to 1/2 mv squared, multiply 2 on the other side, which would cancel out the 2 on the bottom, divide it by the m, and take the square root, and we have velocity is equal to the square root of CR squared over m. For E, they wanted to fully describe the subsequent motion of the ball from the time it reaches the center of the planet. So what I said is that it will oscillate around the center of the planet. It will oscillate around the center without damping, due to the fact that there's no energy loss. And this is also due to the fact that the mass surrounding the ball through its motion would apply forces onto it. So it would apply forces. So since it would apply forces around it, we would sort of have a slingshot effect, as it would keep on going back and forth. And finally, as like I stated before, our quote-unquote little foreshadowing is that we have F is equal to negative kx. So that's very, very similar, or F is equal to negative CR, and that's very, very similar to F is equal to negative kx. So it's very, very similar into a spring, and due to the fact there's that oscillation, due to the fact that the mass is constantly surrounding it, and then the forces are constantly changing. The forces that are acting on the ball would be surrounding the ball and thus influencing its path due to the forces being applied. So keeping that in mind, considering that's oscillation, we could establish this as a period question, which is T, or a period question, which is T is equal to 2 pi square root m over k. In this case, our k, or our constant of this oscillation, would basically just be c, which I substituted into the bottom. In this case, our constant would be c, as I wrote over here. T is equal to 2 pi square root m over 4/3 pi g density times mass. And then just canceling out the two m's, we have t is equal to 2 pi square root 1 over 4 over 3 pi g multiplied by density in mass. And that is how you solve the APPC gravity problem. Thank you.